So welcome everybody to the fourth day of the conference. And it's running very smoothly so far. Thank you all for the organizers for getting us down to the beach yesterday. So the first talk of today is going to be by Ramanayake, who's going to talk to us about algorithmic complexity of substructure logics through path sequences. Ravanta?
Thanks. Thanks a lot, Nick. Thanks very much to the organizers for the invitation. It's a real pleasure to talk at BLAST2022. I've heard already twice that everyone's been to the beach. So yeah, so it's really, I'm also sorry that I'm not there, but also sorry for myself. So, okay, let's begin. Okay. Yes, there we go. So let me start by giving a summary of where I want to go in the talk as a whole. And you'll already see that I have highlighted some words, and that's because I'm aware that the audience is quite diverse, brought together, you know, by some common topics, but also having quite different interests and backgrounds. And yes, can you hear me?
Yes, we can.
Okay, all right. And for that reason, I'm going to explain a lot of the terms that I'm using here, right? But let me start with a high-level overview, so you know where the landscape. So this talk is about upper bounds for deciding valid statements of substructural logics. So substructural logics means, well, we certainly know classical propositional logic, and now we want to talk about logics that are more expressive than classical logic. And in terms of the algebraic models, you could, we saw even some talks before, you could think about residuated structures, right? These are the models of the substructural logics that we're going to be looking at. And there's a notion of theorems of these logics. And we want to decide if a given statement is a theorem or not. And we're going to say that the set of all statements is coming from some set X, and it's going to be there's going to be a well quasi-ordering. It's going to be a well quasi-ordered set. And then that's going to set the scene for talking about talking about bad sequences, control bad sequences, which I will define again, on the power set of X with respect to the majoring ordering. And where do these sequences come from? Well, they're generated by the proof system, because you give me a statement that you want me to test. And you could imagine that you think about going backwards in a proof, and that means a proof system consists of some rules, which means that when you prove a statement, it came because you proved some set of premises, finite set of premises, and that's how you go from a single statement to a set of statements, and then you iterate it backwards, right? So that's where we talk about the power set, and we want to talk about how far we need to go, right, which is talking about the maximum length of these controlled bad sequences. And the talk is concerned about getting tighter bounds for fragments of the logic. So we can we will already see that the full logic we want to look at has very high complexity, and then we will look at results which give tighter bounds or sharper bounds for fragments of that logic. And these tighter bounds comes from conditions on, we talked about the power set of X, and we can talk about downsets on the power set, and in the ideal decomposition and conditions between ideals from adjacent elements in the sequence. It's that condition that can be used to compute a shorter weakness or the tighter bound. And we'll also talk about how this relation ideals, what it means in terms of the proof system. Righto. This work is a collaboration with Adrian Puerto-Aubel and Amir Tabatabai, both of whom are from Groningen, the University of Groningen, as myself. All right, classical propositional logic. We know it. We can talk about Boolean formulas, which means that the language is propositional variables. We have this very familiar Boolean connectives. And the decision problem, the validity problem, is saying you give me a formula, a Boolean formula, Is there a tautology? And there's an obvious algorithm using the truth tables, is that you check that for every valuation, every possible valuation, every assignment of true or false to each propositional variable, does the formula evaluate to true? If so, it's a tautology. We know that if you gave me a formula f of size n in terms, for example, of number of symbols, we know that it has at most n different propositional variables. So we know how many different valuations there are. If you fix the valuation, we can check whether it evaluates to true or false in around n steps. So already, if you considered all the valuations, you'd say that validity is in x time, which means that you need order of exponential many steps to determine if it's a tautology or not. If you did it a little bit more carefully, not only you looking at one valuation at a time and not storing all of them, you get p space. And also we know, of course, that it's in co-NP. Right. However, classical logic is not enough, in the sense that there are a lot of interesting things we want to reason about, and classical logic just does not give us this expressivity. So for one example here is, let's say $1 and $1 implies ice cream. In classical logic, we can conclude from this that $1 implies ice cream, right? But we don't want, in real life, we want to say other things, right? We want to say that $2 gets me an ice cream, but $1 does not. And substructure logics provide a means of modeling such situations. And they do that by including connectives that lack the nice structure or the strong structural properties of classical logic. So you can imagine this connective dot or times, which is sort of gathering resources. So $1 times $1 or concatenated with $1 really means $2, and in particular does not mean $1, right? So you cannot make, you cannot conclude the line below. Similarly, in classical logic, you might say socks and shoes means I'm ready for work, and therefore by commutativity, we would say that shoes and socks makes me ready for work. But in real life, we don't want this situation, right? So we would like a connective which does not commute, for example. And in this way, we can start dropping various structural properties of the classical connectives. And this finds a lot of applications in computer science, in linguistics, for example, and also as interesting mathematical objects. Of course, there is a cost to saying that the logic is more expressive, because it means that it's typically more algorithmically complex. So since we're interested in the validity problem, we saw with classical propositional logic, we saw what its complexity for deciding a tautology, deciding validity. Intuitionistic logic, whose models are Heyting algebras, we know it's in P space. And with substructural logics, where you can imagine adding, structural connectives that don't have these, logical connectives that don't have these structural properties. I've given you a specific example here where you consider adding a structural connective that does not have the weakening property, right? And immediately you go from intuitionistic logic to the logic, let's call it FLEC, F-L-E-C, which has Ackermannian complexity. And in fact, you can show that you cannot do any better. You cannot, there is no smart algorithm you can have which can decide validity faster than that, because there's a lower bound as well. And in case you're curious but haven't seen it before, this is an example of an Ackermann function, which is computable on all values, right? For all natural numbers, clearly it's computable, because you can see that whenever you can evaluate a function, either it goes down in the first coordinate or it goes down in the second coordinate. So this function is clearly computable. However, this function grows very quickly. So for example, this function A evaluated on 4,2 already has almost 20,000 digits. I remember hearing a long time ago that this was an exercise that would be given to first-year computer science students, where they would be given this seemingly simple description of a function and asked to calculate some small inputs. Well, okay, so I talk about this simply to show you that the FLEC logic that I mentioned before, which is very close to intuitionistic logic in its proof rules, but we add a substructural connective and we get very, very high complexity. Here's a survey of just some substructural logics. Of course, a lot more is known about many logics and their complexities, but here is the FLEC, which I mentioned, which is Ackermann complete. And then Schmitz, very recently in 2016, showed that if you consider from FLEC, if you consider the fragment without the lattice connectives, without the meet and without the join, then you can decide, for those formulas, you can decide validity into X time, right? Which is in this set of functions given here. And that's, it's already a big class, but compared with the Ackermannian, this is a big drop. And the argument that Schmitz uses in his 2016 paper is via a series of automata theoretic reductions from one to the other, to the other, to the other, until you reach known problems. Recently, my collaborators and I, we looked at extensions of FLEC, right? So FLEC means it's standing for full lambic calculus, if you're curious. The E means the substructural connective is commutative, and the C means that it has contraction. So we look at FLEC and flu. Flu means that there's no contraction now, but you have weakening. And you can consider large, infinitely many extensions of these logics, and we obtained a hyper-Ackermannian upper bound. So we've now gone beyond Ackermannian to hyper-Ackermannian. And looking at the two results, the top two results you see on the screen there, where Urquhart has it for with the lattice connectives, and Schmidt shows that if you take the fragment, you have a drastic drop. A natural question to ask is, what happens if you consider the lattice connective free fragments of these logics given by this theorem, right? And that's a starting point for understanding how we can, how could we get tighter upper bounds for these fragments. Right, so what can we say about upper bounds for their fragments? And Latzig and Schmitz, in a paper that appears online before but published, I believe, in 21, the ideal view on Rakov's coverability technique, instead of the automata theoretic techniques that were used for the 2016 paper, here they use algebraic arguments to obtain these tighter upper bounds. And the setting there is no longer a single logic, but there is transition systems in general. And let me emphasize that this paper, LS21, is the main source and the inspiration for, I say, this talk, but also for this work, the collaboration work that I've been talking about. Right, so what we do here, what I'm going to talk about is looking at these arguments in the setting of substructural logics and proof systems. Right, so there are all these transition systems, but no, I'm interested in my substructural logics and proof systems, and we want to see, first of all, what we can clarify the arguments in this setting, and also abstract, because we want to ultimately go to these other logics that I mentioned, all these extensions, where this out of the box, the result certainly does not apply. So can we see how to abstract the argument, extend the argument, and apply to all these logics? That's the driving motivation that I'm talking about in this talk. Okay, so what are these proof systems that we're looking at, our transition systems? Okay, so a proof system consists simply of a set of proof rules, and the proof rules are used to derive the theorems or the validities of the logic. So if you have a proof system for classical logic, you have some rules, and you can mechanically use these rules and derive from theorems. You can derive more and more complicated theorems, and in this way, you can, if you spot the proof, you can derive every theorem that you wish. So for the rest of the talk, let X be the set of statements in the language of the logic, right? The set of things that we are interested in checking. Is it true? Is it a validity, or is it not? If you're familiar with some proof theory, you can read these as the set of all sequence, right? I'm going to put the proof theory specific things in blue, but if you omit them, the talk will still run. Okay, so let's get some notation here. So we're going to talk about a finite subset of X union element X. And the first line says that X is provable from S. You could say X is provable from the assumptions S. If you put a superscript K there, I mean that X is provable from S in at most K steps. And if I put a 1, it means that X is already among the assumptions, or I can get to X from S or from some subset of S by applying a proof rule. Okay. In your head, if you want a picture, you can look at these proofs as trees, right? Because our proof rules can have multiple can have some number of premises. So the thing that I want to prove is at the bottom, is at the root, if your trees are growing upwards. And as you keep applying proof rules, you start getting this tree. And then if you look at the leaves, that's where S comes from. If I collect all the leaves, that set of statements is S. Okay. If you have, by the way, if you have any questions, I probably won't see it. So please interrupt me in some way. Right. So our task is to decide if you give me an X. Our task is to decide if there is a proof of X, and we're interested in the case when X is provable from no assumptions. From the empty set of assumptions, can I prove X? Or equivalently, if I consider all those sets from which I cannot prove X, is the empty set among that set? And the overall plan is to construct a sequence of over approximations of this set here, of those S's that don't reach X, and show that these approximations stabilize after a finite number of steps. So we don't get anything new after a finite number of steps. And then the problem, it's sufficient now to look at that, at the point that that's stabilized and check the membership of the empty set. Of course, all these checks take time, right? I mean, you have to count how expensive is it to generate each new approximation to check for membership. But it turns out that the dominant term in the complexity is the length to stability. So that's the key thing we're interested in here. And if you get that, all the others are small compared to that. Right. So just some preliminaries. Let's consider a quasi-ordered set. So we're going to talk about a sequence being good on this set with respect to this order. If there are 2 points in the sequence, a later element and an earlier element, such that the later element is greater or equal to the earlier one. If the sequence has this property, we say it's good, otherwise it's bad. And we said that the ordering is a well quasi-ordering if there is no infinite bad sequence. Every infinite sequence is good. Every infinite sequence, there is one element, a later element that dominates an earlier element. There's an alternative characterization of well quasi-ordering, which we'll also use, which is that there is no infinite chain of downsets of X. And it's not too hard to go from one to the other. In one case, you'd look at, you would choose elements from the set difference to get the point sequence on X. And in the, if you give me a sequence on X, you take its upward closed set and take the complement. And that's how you generate the downward the downsets for the alternative characterization. We're also going to be, if you give me this quasi-ordered set and this quasi-ordering, this well quasi-ordering, we're going to define the majoring order on the finite power sets of X, which is that set S is less than T under the majoring ordering. If you, for whatever element you pick from S, I can find an element from T, which dominates it at the low level. All right. And it's easily checked that the majoring order on the finite power sets is a well quasi-ordering. Right. Right. So now what we're trying to do is we're trying to find the structure that we need that is going to allow us to push, in abstract sense, push through these tighter bounds. And we saw what a proof system is in your head. Once again, if you know a sequence system, sequence calculus, for example. And now we're going to talk about an ordered proof system, which means that our set of statements is a well quasi-ordered set. We say that from you pick an element that is above another, then from the upper element, we can derive the lower one. We have a finitary condition because I did not say anything about how many proof rules we're allowed to have. There's no restriction there, but the restriction is that you choose S union X, right? Well, the number of there's a small typo here, I'm afraid, but you choose an X, and the S's that can reach S from the S's from which you can reach X in a single step is finite. So I'm sorry, there's a small typo. It's not wrong, anyhow, it works. All right, and compatibility says that under the majoring ordering, if T is greater than S, and from S, I can prove some statement in one step. Then from the T that is above it, I may not be able to prove X, but I can prove some element that is above X. Right? So compatibility means that the proof system is talking, the one-step rules are talking with the well quasi-ordering. From S, if I can prove X, well, then from T, I can prove some element above it, which means that from T to this element above it, Y, is a proof rule in my proof system. These are the conditions of the ordered proof systems. And in blue, you can see I've written, if you're familiar with some proof theory, what it means in the proof theory world. Here's an example of a ordered proof system. So you gave me a formula F. We can consider subformulas of F. Let's say there are D many. And we can define our set X as a D plus 1 tuple. And the first coordinate contains some n1 copies of F1, and the D coordinate, so the first D coordinate just has some multiplicities of the subformulas, and G is also another subformula. And then we can define an ordering as shown here. This is actually just a way of formalizing the sequence and the contraction rule. So I don't think we have to dwell more on that. The point is, here's an example of an ordered proof. Well, this set is a well quasi-ordering, and if our proof rules are nice, then we get this ordered proof system. Okay, the example seems not to have come for the talk, but that's fine. So, for example, LEC is an ordered proof system. Right. Let's see what these over approximations of this set are. Remember our plan. You've given me an X, and you want me to test whether X is a validity or not. And the plan is we're going to compute the sets S from which we cannot reach X. And then later on, if once it stabilizes, we can test in that, in that finite member, we can, when it stabilizes, we can test whether the empty set belongs there, right? All right, so here are the approximations. We consider the sets from which you cannot reach X in one step. The sets from which you cannot reach X, simple X in 2 steps. You cannot reach simple X in 3 steps. In fact, it's a little bit more than that. It's not only am I saying you cannot reach X, but you cannot reach any element above X, right? So cal d k is the elements from the power set such that you cannot reach any element above this X, simple X that you've given in K steps. So we may observe that the cal d k is a down set. So, so suppose we have this situation that is S is smaller than T, and T is in the cal dk set. Well, if S is not there, then by the definition, I must be able to reach X in K or less steps. And by compatibility, I can go from S goes to X, I can go to T goes to some element above it, which would contradict the membership of T in DK, because in CalDK, because CalDK consists of the elements where you cannot reach an element above. Right. So we know that the power set with the majoring ordering is a well quasi ordering. So which means that we know that every decreasing chain of downsets is going to it's going to stabilize, and therefore in the end the game comes down to saying, okay, once it stabilizes, we're going to check for the empty set membership. That's the plan all the time, and the point now is how big can L be? That's really going to be determine what is this complexity. Well, so what is this? What is the maximum value of L? In general, there is no maximum length for bad sequences. And a simple example can be given here. Let's take a concrete example. This is the usual coordinate-wise ordering, right? Independent coordinates. And you can already construct for any n, you can construct a bad sequence that looks like this, right? And what's the point here? So from 1, 0, I can go to 0, n, right? And I want to make sure this sequence is bad, right? And clearly 0, n is not larger than 1, 0. And then afterwards I could decrease, safely decrease, right? And the point is that if you allow me a big jump, I can have finite but arbitrarily long bad sequences. And you can do a similar game if you want to consider it on the power set. The point is that we're going to have to, somewhere or the other, we're going to have to ban these big jumps. And I can already sort of give the anticipation that if you just consider sequences you don't know much about, well, you can't ban these big jumps. But if you know that your sequences are being generated by some process, for example, by the proof rules, and then you say that proof rules don't make things much bigger in one step, well, then that's how you know that my jumps cannot be big. All right, and that's what is formalized here, this notion of what is known in literature as controlled bad sequences, right? And what can we say? So a control function G is an increasing function. Okay, suppose that we have a norm on our set X, okay, some sort of reasonable finite condition, which is holding in the case of our interest. Well, but here is what I mean by saying the bad sequence is controlled. So the first element, we're going to say a bad sequence is Gn controlled if the first element x0 is smaller or equal to n, and the second element is smaller or equal to Gn, and the third element is smaller or equal to Ggn. And in general, the kth element is the kth composition of G starting with n. Okay, so my jumps are at most bounded by this function G. Okay, and it's not hard. If you tell me that I have a controlled bad sequence, you can see that there is a maximum length. No, let me put it this way. You can first, it's very easy to see now that these sequences are finite. But even if you if you choose any control function, be it a polynomial function or up to a primitive recursive function, but even if it's a polynomial control function, in the concrete case we considered, the length is bounded by an Ackermannian function. Okay, and you can't do better. So what is this telling us? That yeah, that already in this setup, we sort of were doomed in worst case to have really, really long bad sequences. So what that means is that our transition system or proof system is going to require a further, or our logic is going to require further restriction if we want to see sharper bounds. And that leads to omega proof systems, which is going to extend the ordered proof systems with further conditions. let's put some notation here. Is you give me a set T, a subset of X, right? That's the set of our statements. And we're going to say T hat means you extend T with the statements you can prove from T. Okay, you give me T, you extend it with things that you can prove using the proof using a single one-step proof rule. And we talk of an omega proof system as being an omega proof system as being an ordered proof system where we also have equipped with this omega function, which is a function from the ideals of X to a set V, to a poset V, satisfying these conditions here. Our omega function is going to be monotone in the sense that you take two ideals that I is smaller or equal to J, then omega I is going to be less than omega J in this poset. A lifting condition. So let's parse it first, which says that, well, you gave me a set S, and in one step I can go to some statement Y. Suppose that there is an ideal that intersects S. That means that there is some ideal J which is contained in the consequences of S union I, or in the downset of that, right? Okay, and this J, I know something about this J. It contains the Y we obtained before, and also its omega set is which says something about omega set. All right, but okay, informally, what we are saying is that if you give me from some set S, I can go to a Y, right? From some set of premises, from set S of premises, I can conclude Y. Then you can choose one of those premises, not all of them, right? Let's say one of them. You can choose one of those premises, increase that premise to some element above, keep the others fixed, and you can still get a legal proof rule. All right? Think of a binary rule. That means two premises get to a conclusion Y. Just one of the one I fix, and the other one I lift from wherever it is. I lift it up, and I want to now use those two elements to get some new Y prime. And I want this. So it's actually saying more than that, right? Because the condition is also referencing ideals, where I'm talking about the points. But that's the intuition of what this lifting condition is. From the proof theory side, you'll be familiar that multiplicative rules or the context independent rules satisfy this property, right? Because you can change one premise and you don't care, you still get a rule. Additive rules fail this, because when you change one premise, you have to change the other premise as well. Right, so we can define an omega proof system taking the example we saw before. Remember this formalized sequence. And right. Right, and remember that these elements of X contain multiplicities of each of the subformulas, right? And if you take an ideal, in some coordinates, it's going to be bounded, right? There's going to be a multiplicity such that you don't get anything above it. But in some coordinates, it may be unbounded. And the omega function here is just picking out the positions or the coordinate positions where I is unbounded. Okay, all right. No, I think we can come to the lifting if you want to see how the lifting works here. For the moment, let's just say, well, this is an example of an omega proof system. Because already from here we're in the position where we can start attacking these tighter bounds, right? Let's see what we have so far. We have approximated the set. This is a kth approximation, right? Cal dk are the elements of the power set from which we cannot reach any element above X. And what we're going to do, if I look at the statement of of the lemma here is that we are going to find from Chaldees consists of elements from the power set. Now we're going to find a downset of X whose ideals have nice properties, right? So we're coming down from the power set level. We're coming down to the level of X, or downsets. So from downsets of the power set, we're coming down to downsets of X. Right. So in particular, our aim here is that we're going to get a sequence of downsets of X, and we're going to say that you pick an element in this. Let's say you pick some decay in this sequence, okay, and we consider its ideal decomposition. Let's say I is one of the ideals in the decomposition. We're going to say this is proper, K proper, if I, which is in the decomposition of dk, is not in the decomposition of dk plus 1. That's the definition of being K proper, a K proper ideal. And what we're going to show is that we're going to extract this sequence of downsets of X such that in every set, whenever you find a proper ideal, that means an ideal that is not seen in the next element, that's a proper ideal. Well, then there is an ideal in the set before it, which has a greater omega set. Okay, so that's the control on the ideals via the omega function. Right. We can say something more about what these decays are, right? Because we are considering these decays come from the ideal decomposition, from the simple D's come from the decomposition of the Chaldees, right? So you give me a Chaldee like this, I can decompose it into finitely many ideals represented like that, where this decay is a downset, right? And we're going to pick certain these such downsets to make our sequence. All right. Without going into further into details of this, let's just let's see what this result is doing for us. It means that if you pick an element, dk plus 1, and if you pick any ideal from it, that ideal does not appear on its right. It's the proper, it's a k plus 1 proper. And there exists an ideal to its left, that's in dk, which is proper. So sorry, this should be dk plus 1. J does not appear in dk plus 1. And what's more, the ideal that we found to its left is greater than the one we chose, right? So that's that we could call take home 2, is that whenever you choose a k plus 1 proper ideal, it is omega controlled by some ideal in the preceding set. So what Lutzig and Schmitz do is they assert this property explicitly. But here, what we've done is we wanted to understand what do we need of our proof systems that we get this omega monotonicity. Right. And now suppose that we computed these approximations, we extracted the set, the downsets of X as we saw in the previous lemma. Let's see how the 2x time upper bound comes from here. So here we are actually going to consider a concrete setting, right? It could be the sequence that we formalized before, but for simplicity, we are just going to consider X to be this ND, and where the ordering is the usual coordinate-wise ordering. And that's because the calculation is dependent on actually the set. The counting that we want to do is dependent on the set X. Okay, so now we're going from the abstract setting to something more concrete. And in this case, we're going to set our omega function from these ideals. You give me an ideal from the set, and we want to identify what are the coordinates where it's unbounded, and that's its omega set. So for example, if we had this KL, the KL tuples where K is bounded by phi and L is not bounded, then the omega set contains a single element, so curly brackets there, contains a single element containing 2. On the other hand, if we had chosen the ideal that is unbounded in both coordinates, then its omega set would be 1 and 2. Right? It will consist of 2 elements. And if it was bounded, let's say by 5 in both coordinates, then the omega set would be empty. Right, and now this is what we're going to do. We have, from the Chaldees, we have got this sequence of these downsets of X. Right, we're going to look at the far right corner, and we're going to pick an ideal from the dn minus 2. Right, we're going to pick a proper ideal, I n minus 2. Right, you'll understand that why the index we have had to go to n minus 2, because proper ideal means that it does not appear in the next one. Right, so we couldn't have taken the rightmost element, but we've taken the one next to the rightmost. Right, so we choose an ideal I n minus 2, which has a maximal omega set. Now I'm going to look to the D set next to it, which is dn minus 3 to its left, and I'm going to choose an ideal from there. And you know that there is an ideal which satisfies this property, because we already saw this, right? If you're looking at proper ideals, if you choose n minus 3 proper ideal, then there's a if you choose an n minus 2 proper ideal, then there's an n minus 3 proper ideal whose omega set is greater. The existence is by the previous lemma. So in this way, we can start choosing ideals all the way up to D0. Right? And as you do this, you note, so sometimes sometimes the omega set will, in general, you may expect to increase, right? It may stay flat like this, then it might increase up by 1. Then it'll stay flat, then increase up by 1. So it's like climbing a stairs. And so you could imagine the point at which you are forced to do a climb. You know, the last element, if you're climbing up the stairs, the last element before which the next one is going to be on the next step. So well, we have this property then that let's say we're climbing the stairs. On the stair we are currently, we have this point which is of omega set, capital omega. And then when you climb the stairs, we go to something that is strictly greater than omega, right, by the construction. And we know on the flat part of the stairs, by the construction, there is no proper ideal whose omega set is greater, right? Because if there was one, we'd have already climbed the stairs then. Right. All right. So first thing to notice is that we can see how many steps there are, right? Because our omega set is a subset of 1 to D. It has at most D elements, and where we keep adding. So from the empty set all the way up to the full set, there are at most D plus 1 steps. So the next thing we have to do is to say what is the breadth of my stairs. And the argument, which I have not included here, is you say, well, you know, what's your worst case? How many distinct proper ideals could you have, right? And what you have to do is you have to say, if I have a proper ideal in the middle, you know, on the long part of the step, you can argue that its size is going to be bounded by the first, you know, the set of that has the first point on the flat part of the stairs. And right, yeah. So and you know that for every ideal that you've chosen here, you know that in omega, you can show that in omega positions it's unbounded. So that means that you have only choice of ideals of finite values in the D minus omega positions, right? And that's where the exponent D minus cardinality of omega comes in, right? And in this way, you can bound the breadth of the step. Now, this approximation, okay, so actually I'm going to draw one more fact to you that in this way you can, yeah, so if you know what the size of your Ds are, the norm of your Ds are, then you can keep iterating this, and you can compute the value. Of course, actually the Ds we extracted from the cal Ds, remember, right, in the previous lemma. So we don't actually have that good a control on the Ds, but it turns out that we can bound each D value by its cal D value, right? And we can show that, in fact, the cal Ds were GN controlled. So that means that I can bound any dk by the cal D naught value. And then I can take the addition after all of these steps. And you can see what we computed here is like the inductive step, right? So this d to the minus omega is what is being seen here as an m+1, right? With some arithmetic, you can show that the sum we can show that this is bounded by a function that looks like this, and now you can see that the size of the proof system is coming into it. And yeah, and okay, so in our particular, let's just look at what values we want to substitute here. N, remember, is a starting value, so that's the D naught, cal D naught, which we can calculate. And the number of steps is the dimension, right? It's determined by the number of subformulas. And so from this exponent of the factorial, we get that this function is bounded by 2 to the 2 to the x, which is the 2x time bound. Right. So that's the abstract setting that we want to extend now from the we had in our mind sequent calculi and the results that are known for LEC, and now we want to see how can we extend them to hypersequent calculi in this abstract setting. We also want to consider what logics and their fragments in particular we can get Taiter-Browns for. So I talked about extensions of Fleck and Flew, but you could also imagine modalities or classical full-Lembeck logics. So many non-classical logics where now it's reasonably well. You can see proof theoretically we have a handle on what this omega monotonicity is, right? So that gives us some sort of way of understanding already. Could this Taiter-bound work? I'll close there, and I welcome your questions. Thank you.
Thank you very much for the very interesting talk. Are there any questions or comments? Yeah, thank you.
Thank you very much for this very interesting talk. So the result, the main result, just to check, it's for the case without the lattice connectors because they are additive. Is that right?
Right. That's right. That's right. So the additives fail this omega monotonicity condition, or the proof rule equivalent that I mentioned. Yeah.
Okay, but you're now thinking of investigating the non-commutative perhaps as well. And my question is, when you go in that direction, do you expect the complexity to go higher or lower?
Yeah. What we know of the upper bound for extensions of Fleck and Flew is already hyper-Ackermannian, and it's in a sense it's the argument that gets you the Ackermannian bounds on sequence. When you go from sequence to sets of sequence, the length goes from Ackermannian to hyper-Ackermannian, and now we're saying from that go down again to fragments, right? I would think I wouldn't think that it would still be 2x time, but I'm not sure actually where it would be. But I don't know where it lands.
Thank you. Other questions? Maybe I have a question. So if you establish an upper bound if you assume that you have either exchange or weakening, sorry, either a contraction or weakening, what if you further add other rules, other structural rules, is there any hope that you can fine-tune the methods so that you can bring the upper bound even lower?
Right. So that's exactly what we want to study, right? So when I mentioned the hyper-Ackermannian upper bound, that's taking Fleck or Flew as the base calculus and adding, and the result applies whatever structural rules you add to it. Okay, so the hyper-Ackermannian upper bound is for Fleck plus any structural rules, finite many structural rules, and same with Flew. And now the question then, as you say there, is you take one of these, structural extensions of Fleck, and you take a fragment. Then, what is the upper bound can we get? In analogy with Fleck going to LEC, can we also witness a great? Can we witness a reduction in the upper bound? That's precisely what we want to look at.
So yeah, do you think that you need to develop new methods for doing this, or you can fine tune the existing methods if you add further rules?
I think the jump is actually going from the sequence to the hypersequence, right? So whether you want to see this having more rules or not, yeah, it's just you could look at it in ways. Yeah, but it seems that we will need to extend the technology. So in fact, this abstraction that we've got here is also to isolate exactly what we need in this logical setup and what we can extend. But it looks like our hope is that, I mean, in the end, we want to have this, we want to set it up as in an abstract enough way that whether you're looking at sequence or hypersequence, most of it carries on. But yeah, I think it looks like a generalization is required to come to this point.
Thank you. Any questions from the online audience? Okay, so let's thank Ramanayake again.